Hello friends, welcome to another video from C Field Academy where we learn together from each other. So today's topic is deadlock from operating systems in the context of computing or computer science. So let's get started. So first things first, the details that I have in this video is more or less taken from the operating systems concepts book, which is by Silverscratch, Galvin and Gagne. This book has been a very good material for undergraduate study. Even when I was an undergraduate, I used to use this book, so hence I thought I'll just cover the topics of deadlock based on this book. So if you have a copy of it, and if you want to go into the detail, I would recommend definitely to go to chapter 8 in 10th edition, or probably chapter 7 in the older editions. So let's see what we are going to cover today. So first we will start with the basic introduction or definitions of process, thread and resource. We'll try to differentiate them, and we will understand these concepts from the context of computing, or what it means in a computer system. Then we will see how a resource is being used by a thread. Basically there are a few steps through which a thread uses a resource and then releases it. Then we will start with the definition of deadlock as well as Livelock. Little bit about Livelock. We won't cover much about Livelock because the video is more about deadlock. Then we will get to the most important part of the video, which is necessary conditions for deadlock. These are very important because the whole concept of deadlock moves around these four conditions. Then we will see how do we handle deadlocks, basically various techniques to handle deadlocks. We will go deeper into deadlock handling mechanisms, where we will see deadlock prevention, deadlock detection. We will also see a concept called as a resource allocation graph, which we can use to detect deadlocks. And finally, before we end, we will cover deadlock recovery, and we will end with some review questions. So friends, let's get started. So let's see what a process is. So as we know, we have a computer, or we have a computer system, and in a computer systems there might be different programs. Let's say we have Microsoft Word, which we use to write Word, or maybe a video player, which we use to play a video. So all these, when they run, they become a process. The system allocates a process ID, and then the process runs, and during the running of process it might need some other resources to perform its task, and then finally, once its purpose is fulfilled, it would exit. So a process internally may contain one or more threads that might be running concurrently. So what is a thread? So thread is basically a smallest sequence of instructions, or a smallest unit of execution within a process that can be scheduled and that can run independently. So normally a process contains more than one threads which are running parallelly. Let's say we have a process here. Let's say I have a video player. Now the video player, one of the tasks could be to display the video on the screen. Another task could be to display, or to basically broadcast to the audio device so that we can hear the audio. So we can say there are multiple threads. One thread displaying the video aspects of it, and another thread doing the audio aspects of it. And we might also have another thread that might be doing logging of how the process is going on. So this was just an example, but in some sense in this video you can assume that process or thread is the same, or the whole concept of deadlock applies to threads per se. And then comes resource. So resource is a physical or virtual component in a computer system that can be allocated to a thread. So resource can be, let's say monitor is a resource because monitor is used to display a video. Keyboard could be a resource, and similarly we may have, let's say CPU is a resource because programs need CPU, programs have to be scheduled on the CPU. So these are few resources, and resources can be of several types, and each resource might also have multiple instances. Yeah, some examples are CPU cycles. If you have multiple CPUs, then we say that we have multiple resource instances of CPU. IO devices like monitor or the speakers, let's say, files that are on the file system, and also the network. So all these could be resources, physical or virtual resources. So next we come to how a resource is utilized by a thread. So usually resource allocation involves 3 steps. Because resources are shared, there are so many processes running on the system, there should be a specific process of request, allocation, and then release. So the first step of resource utilization is request. So a thread has to first request the resource to the system. So a thread will ask, please grant me this resource. If the resource cannot be granted, the thread must wait till it's available, and during that time it might be waiting and not doing nothing. So an example could be, let's say there is a file, shared file or a log file that is being written by multiple threads, and one of the thread wants to write to it, so it will ask permission or ask to hand over the file descriptor to the thread. And if the file is being written by some other thread, the process or the thread has to wait till the file is released by other threads, because as we know, writing to a file simultaneously by multiple threads is not allowed. So once it receives the resource, or once it has the resource allocated, it must use it, which means it must, let's say, write some content to the file, and once it has finished using the resource, it has to then release it so that other threads can use it. So let's say our file writer example here, after writing to the file, the thread has to release the file descriptor to the system so that it can be then reused by multiple threads. So there is this 3-step process of resource utilization, and all the threads or processes in a system have to follow this these steps, this protocol. Cool. So let's see what a deadlock is. So as we have already seen, there are processes and processes requesting resources. There might be a situation that occurs when processes are blocked. Why? Because they are waiting for assignment of some resources, and those resources are allocated to some other processes. So when we have a set of processes which are blocked because each process is holding a resource and then waiting for some other resource, then we say a deadlock has occurred, because neither of the process are able to proceed and all the processes are stuck, and there is absolutely no work getting done in a system. None of those processes can continue and then perform some task. So here is an example. We can see normally processes are represented by circles. Here we have P1, P2 and P3, three processes, and then we have 4 resources, R1, R3, R2, R4. So P1 has resource R2 over here, and P1 is asking for R1. P2 has R1 and P2 has 1 of R2 and it's asking for R3, whereas P3 has R3 and waiting for R2. So if you see, all these three processes are blocked, they cannot proceed because each one is waiting for some other resource to get allocated. So this is a situation of deadlock. Now, similar to deadlock, there is another concept called as Livelock, which we probably don't cover much in this video, but it's a similar situation where the processes are not blocked, but they are essentially not making any progress. They attempt an action, and then the action leads to failure. So a simple example given in the book is when we have, let's say, two people want to pass through the hallway, because the hallway has very less width, only two people, only one person, less width, and then they are on to, they collide with each other. But then one person turns right, but the other person also turns left, so they again collide. Under such situations, they are not really able to fulfill what they are supposed to, which means they cross the hallway, and they just keep following each other and facing each other and not able to cross each other. So such a situation is a Livelock. Alright, now the important part of the video, which is the necessary conditions for a deadlock to happen. And remember, all these there are 4 conditions, and all 4 conditions should hold simultaneously. If any one of it is held, deadlock will not happen. So let's see what these 4 conditions are. So the first condition is mutual exclusion, which means there must be some resources, at least one resource is non-shareable, which means it cannot be shared simultaneously by processes. Only one process can use it at a particular time. Second is hold and wait. So every time when there is a deadlock, there is a thread which is holding certain resources and waiting for additional resources that are being held by other threads. 3. No preemption. Now the no preemption means that resources can only be released by the process. Nobody else, and not even the system, can preempt the process or preempt the resource or snatch away the resource from the process. And once the process has been allocated, once the resource has been allocated to the process only can voluntarily release it after it has completed its task. So nobody else or no one else has the authority to snatch away the resource from the process. And fourth and the last condition is there has to be a circular wait of threads, in which one of the thread is waiting for another resource. And so basically there is thread 1 is blocked because of thread 2, thread 2 is blocked because of thread 3, and so on, and finally the last one is waiting for thread 1. So there is a circular wait in which every thread is holding certain resources, and other resources for which it is waiting for is blocked by the next thread, which means whenever there is a deadlock, there always exists this circular wait condition. Cool, I hope this made it pretty clear. Next we will move on to how do we handle deadlocks in a system. So there are a few ways to handle deadlocks and systems, or we can choose one of those handling mechanisms. The first and simplest technique is to just ignore, because deadlocks are not always a real problem. They may not happen that frequently, so we could just ignore the problem altogether, or we do not just do any handling and let the application or the user of the system actually take care whenever there is a deadlock. You might have seen situations where your system is hanged due to some process not responding, and then we end up restarting the system. This could be one of the examples of where the system ignores the problem, and then uh, the handling is left to the user. And this is the mechanism that Unix and Windows follow, because otherwise handling deadlocks could be very costly for the system and might even be very CPU intensive. So the next technique is to prevent or avoid, which means we will always ensure system is away from the deadlock state or will never enter deadlock state. So in prevention, we ensure at least one of the necessary conditions is avoided. It might have issues on how we allocate the resources or the requests for resources. In avoidance, we maintain a safe state of the system. We'll come to more about what a safe state and unsafe state is in the next few slides, but for now let's just take it that in avoidance we always ensure that the system is stay safe, and whenever we see that the system might be going into an unsafe state, we just don't take that step. Then the last way is to let the deadlock happen and let us detect it using some technique and then try to recover from the deadlock. And this is the technique that is used by most of the databases. So cool, let's see in detail these different deadlock handling techniques. So first is deadlock prevention. As we have already discussed, one of the so basically the prevention technique uses the fact that we have to just break one of the 4 necessary conditions which exist when there is a deadlock. So the first is mutual exclusion. How can we avoid mutual exclusion? How? We make resources shareable. But this may not be practical because some resources may not be shareable, but other resources we can make it shareable. Let's say read-only files. So multiple processes or multiple threads can read a file, although they may not be able to write to them. The second condition is hold and wait. So ensure we break the hold and wait condition, which means one way to handle this is we let processes know that they request all resources at once. So whenever they want, you just request all the resources at a point, and that time we can see if all the resources can be allocated, we allocate it to them, otherwise we do not allocate it to them. So similarly, and if the process wants additional resources, it has to first release its resources and then request all over them again. So this avoids the hold and wait condition, because hold and wait condition will never arise where the process is holding certain resources and it is waiting for some more resources. So the third condition is no preemption. So to avoid this condition, we have to allocate authority to the to the OS, so that it is able to preempt the resources based on certain conditions. It's possible that this might lead to some greater losses or greater amount or losses to the work done, but in a way, if we grant authority to the US so that it can preempt the resources and deallocate it from the processes, we can avoid this condition and hence the deadlock. Lastly, the circular wait. So circular wait can be avoided just by ordering the resources from 1 to n, and then having a protocol that resources have to processes have to ask the resources in an increasing order all the time. So in that way we can always we can always avoid the circular wait, because nobody will actually allocate the resource 1. So which means if the processes, let's say P1 is allocating resource 2 and 4, P2 is allocating 1 and 3, so they have to request them in order, which means the first P1 requests for 2, then only it requests for 4, P1 requests for 1, and then only it requests for 3. and let's say P1 also needs 2, so it has to request in 1 2 3 order. So under this situation, if and assume even P1 needs resource 3. So since 2 is allocated to P1, P2 will be stuck here, so P2 won't be allocated resource 3, and hence there will not be any deadlock because P1 will go ahead and allocate resource 3. So these were mechanisms to prevent deadlock. So let's go ahead and see the next item, which is avoiding deadlocks. So avoiding deadlocks uses a concept of safe or unsafe state, and then where we ensure that system always stays in a safe state and never moves to an unsafe state. So if we see the state of the system, we are in a safe state, and only in the unsafe state deadlock can occur. It's possible that in an unsafe state deadlock doesn't occur, but in the avoidance mechanism we just avoid unsafe state altogether, and this sometimes is a huge cost to the system as well. So to do or to calculate if the system is in a safe state or unsafe state, the processes have to provide additional information to the system, and that too in an advance. And as we see, this is a conservative approach, so this processes have to declare very well in advance, I need 2 instances of 1 and 3 instances of 2 and so on, which may not be practically possible. So there are popular algorithms which are used here to detect safe and unsafe state. The first one is the resource allocation algorithm, and the second is the banker's algorithm. In fact, both of these algorithms, because they are pretty important and they are involved, are covered as separate videos on the channel. I would recommend you to go through them. In fact, these are very important resource avoidance algorithms. So moving on, the next item is deadlock detections. So one way to handle deadlock is also to detect the deadlock and then recover from it. And one of the ways is the system goes and periodically checks, is there a deadlock? Is there a deadlock? And then it runs algorithm to check if the deadlock is currently present. And what are the algorithms that are normally used? So there are two types of algorithms, two algorithms that are used. One is the Waitfor graph, and the second is the modified bankers algorithm. So both of these algorithms are related to the deadlock avoidance algorithm that we saw on the previous slide. And the Waitfor graph is used under situations when there are single instance of each resource type, and when there are multiple instances of each resource type, we use the modified bankers algorithm. Cool. So let's see what a resource allocation graph is, because this is a very important concept when we come to deadlock and process allocation, resource allocations. So resource allocation graph, as the name suggests, it's a graph. First of all, we saw this on the first slide when we were discussing deadlock, and what happens in this graph is we represent processes by circles. In this example we have P1, P2 and P3 as 3 processes. Then we have resources are represented as rectangles, and in fact when there are multiple instances of a resource, we use dots to indicate multiple resources. For example, resource R2 has 2 instances, and these are represented by 2 dots here. Similarly, R4 has 3 instances and are represented by 3 dots here. And then we have some edges as well. First type of edge is a request edge. So request edge is a directed edge from the process to a resource, indicating that the process is wanting or needing for that resource so that it can use it for its execution. So So directed or request edges are edges from the process to the resource. So here we see there is an edge from P3 to R2. This is a request edge. Similarly, we have a request edge from P2 to R3. We have a request edge from P1 to R1. Cool. Moving on, assignment edge. So assignment edge is an edge that is from the resource to the process. So this is when that resource is already held by the process or already allocated by the process. So here we see that R3 is already allocated to P3. R2, one instance of R2 is allocated to P1 and one instances of R2 is allocated to P2. So these are directed from the resource to the process. Now how can we detect or how can we check deadlock when we have a resource allocation graph? So here are the stuff. If the graph does not contain a cycle, so the basic idea is to check for cycles in a graph. If the graph does not have cycle, then deadlock doesn't exist. If there is a cycle, there might be a deadlock. In fact, if there is a cycle and resources are just in single instance type, then we are sure deadlock exists. If there is a cycle and there are multi-resource type, there may be deadlock. There may not be a deadlock. So here is an instance. The first example here is where we have a deadlock, and we might see that these are multiple instance type resources, and here we can see that there is a deadlock because R2 is being held by P1 and R1 is held by P2, R3 is held by P3, and each of them are waiting for resources. P3 is waiting for R2, P2 is waiting for R1, and P2 is waiting for R3, and P1 is waiting for R1 to be allocated. So there is actually a cycle which is more or less like this. So this is the cycle. And in the next example, you might see there is a cycle, but there is no deadlock. Now if you see, there is already a cycle here from P1 this way. There is a cycle, but there is no deadlock because the processes can still proceed, and these are multi-resources type. So P2 can execute R1, P2 can proceed, and once P2 proceeds and R1 is released, P1 can also proceed. So this is not a deadlock. Cool. So let's use the resource allocation graph to check for deadlock detection. So one way to do it by using a Waitfor graph. So Waitfor graph is just a modification of the resource allocation graph, where we actually create a modified graph by collapsing the edges and then removing the resources, and this only works for single resource type, which means resources only single instances of resources exist. So here is an example. Now in this example we have a resource allocation graph which looks like this, and we can transform it to a Waitfor graph by removing each of the resources, which means if we remove R1 over here, then we will have P1, there's an edge going from P1 to R1 and R1 to P2, so which means there will be an edge from P1 to P2. Similarly, if we remove R3, there will be an edge going from P2 to P5, which is over here. If we remove P3, then there will be an edge from R4 to R5. Sorry, we cannot remove P3. So because we are removing resources, not processes, sorry about that. So if we remove R4, then there will be an edge from P2 to P3. If we remove R5, there will be multiple edges. There will be one edge from P3 to P4. P3 to P4, there will be one edge from P2 to P4, because there was an edge from P2 to R5 and R5 to P4, so P2 to P4, and there will be an edge from P4 to P1 after R2 is removed. So notice it's a condensed graph from the resource allocation graph, and we can see if there exists a cycle in the Waitfor graph, which means there is a deadlock. In this situation there is a deadlock because we have a cycle over here. I think that's the only cycle that is present, and hence P1, P2 and P4 are involved in a deadlock. Cool. So I hope this helped. So to detect deadlocks, the system has to continuously, periodically, create this graph and then do the checking to see if there is a cycle. And in fact, both can be pretty expensive actually. So one of the other mechanisms is to use a modified Banker's algorithm to detect deadlocks. In this case, resources can be of multiple instance types. In fact, that's when Banker's algorithm is used. So if you have covered Banker's algorithm already, or if you have checked my video, you would see that the Banker's algorithm actually checks for safe state and unsafe state, and in the last step it actually checks when it actually checks if all the processes are completed, or we can simulate the completion of all the processes. In fact, if Banker's algorithm ends up in an unsafe state, which means actually there is a deadlock. So we can use the Banker's algorithm to detect deadlocks. And in fact, the processes that could not be completed in the last step are the ones which are actually involved in the deadlock. Cool. I think the last important topic is recovery, or one of the ways of handling deadlock is to recover from a deadlock. Now this can be very costly at times, because we might have to abort certain processes, which means processes might have done some work and those work might get wasted and might need to be redone. So simplest way is to just terminate the thread, which means just see which thread is causing is involved in the deadlock and just terminate that thread, and then reclaim the resources. And one of the ways is to just simply stop all threads. The other way is to just stop the threads one by one till the deadlock is broken. Another way is to allow preemption of the resource, which means the OS has the authority to snatch away the resources from the process and allocate it to other threads, and this also can be done all at a time or one by one till the deadlock is broken. And we can see there it might be very complex to figure out which process, to identify which process we need to snatch the resources from, what to do, whether to do a rollback, and redo the lost work, and how to prevent starvation, which means there might be a process which never just gets resources, so we need to take care of that situation as well. So deadlock resource preemption can be very complex overall. So I hope this wasn't that long video, and I hope it made the concepts pretty clear. So let's just summarize what we discussed, summarize a little bit what we discussed in this video. So first we discussed processes, threads. In fact, we defined deadlock and even livelock, and we saw the 4 necessary conditions that are required for the deadlock. Then we moved ahead to deadlock handling techniques. In fact, we saw a few techniques here to prevent deadlock, to avoid deadlock, and we saw some algorithms, 2 algorithms for deadlock avoidance. We also saw 2 algorithms for deadlock detection, and then we discussed lastly the recovery, which means to terminate threads and then preempt resources. So thanks guys for watching this video, and before we end, here are some review questions which might you might want to look at, and I would recommend you to post any comments or any issues that you saw with the video so that I can resolve them. And if you have any questions on the topic, feel free to comment on this video and I'll definitely get back to you. So here are a few review questions. So list 3 steps involved in resource utilization by a process in a system. Okay, the second question is a little cooler. So imagine real world situation, which means not in the context of computing, and try to find an example where there is a deadlock or there is a Livelock. The most important question, the next one, 4 important conditions for a deadlock. How can we detect deadlocks in a system? And then list a few issues that can happen with deadlock recovery, why it can be expensive, give some examples if possible. So friends, that's all in this video. I hope you enjoyed this video, and bye bye. See you again in the next video. Thanks.